Somewhere in the Arizona desert right now, there are over 4,000 aircraft just sitting. No passengers, no destinations, no flight plans. They flew for 20, sometimes 30 years. They crossed oceans thousands of times. They carried hundreds of millions of people to places they'd never been, and now they wait in the driest air on Earth for the teams who will take them completely apart. This is not a graveyard. This is mine. Here's a number that will reframe everything you're about to see. The global aircraft recycling market was valued at over $5 billion in 2024, and it's projected to nearly double to $11.68 billion by 2033. According to Boeing's commercial market outlook, the aviation industry will need 44,000 new aircraft over the next 20 years. About half of those deliveries will replace retiring jets. That wave of retirements is expected to generate approximately $52 billion in reusable parts and materials over 2 decades. These aren't old cars being crushed for scrap. These are flying machines built from aerospace-grade aluminum, titanium, superalloys, and hydraulic systems engineered to withstand forces most industrial equipment never encounters. The journey begins at what the industry calls a boneyard specialized facility located in desert regions like Arizona, California, and New Mexico. Facilities like Pinal Air Park, the Mojave Air and Spaceport, and Tarmac Aerosave's operations in France and Spain are among the world's most active aircraft recycling centers. Before a single bolt is removed, every aircraft undergoes a full inventory and assessment. Engineers catalog every component: engine, avionics, landing gear, auxiliary power units, and critically, the complete hydraulic system, rating each for condition, resale value, and reuse potential. On average, a commercial aircraft has a service life of 20 to 25 years. But the parts inside it, the hydraulic components, the pumps, the actuators, are built to aerospace tolerances that far exceed what most industrial machinery ever demands. Before one wrench is turned on anything structural, before one engine is unbolted, before one panel is removed, the first thing the recycling team does is drain every fluid from the aircraft. And this is where the story of hydraulic recovery begins in earnest. A commercial aircraft like the Boeing 737 or Airbus A320 carries specialized hydraulic fluid called Skydrol, a synthetic, fire-resistant phosphate ester fluid engineered specifically for aviation. It's not ordinary hydraulic oil. It costs significantly more than industrial mineral-based hydraulic fluids. It operates under extreme pressures, and every drop of it is recoverable. First, the fluid is drained under controlled conditions using sealed extraction systems preventing any ground contamination. It's then transported to specialized oil purification facilities, where it undergoes microfiltration, stripping out particulates down to microscopic levels, metal particles, dirt, and suspended solids from decades of system operation. Next comes low-temperature vacuum distillation, a process that removes water and volatile contaminants without destroying the fluid's essential chemical additives. The result? Purified hydraulic fluid that can be returned to service either back into operational aircraft or processed further for use in high-pressure industrial hydraulic systems. Oil purification can extend the life of hydraulic components by up to 10 times, according to industry data, making recovered aviation hydraulic fluid one of the most valuable byproducts of the entire recycling process. But the fluid is only part of the story. The hardware that moves fluid, the pumps, actuators, servo valves, and accumulators that make up an aircraft's hydraulic system, are the components that make engineers stop and stare. A single hydraulic actuator on a commercial aircraft landing gear can cost tens of thousands of dollars new. The hydraulic system on a wide-body jet like a Boeing 777 contains hundreds of individual components, each one machined to tolerances measured in microns, tested under certifications that would satisfy the most demanding industrial application on Earth. When these systems come off a retired aircraft in good condition, they don't melt down. They go back to work. The physical dismantling of an aircraft follows a strict sequence driven by value and risk. Engines come off first. They are the most economically valuable components on any aircraft. A single CFM56 engine used on A320s and 737s has a used market value of $5 million to $10 million depending on condition and remaining cycles. More than 99% of engine parts are recoverable, according to Tarmac Aerosave's documented recycling data. Then come the landing gear assembly's complex structures containing steel, titanium, and complete hydraulic subsystems, including actuators, struts, and brake systems. Avionics, auxiliary power units, and flight control actuators follow, each one removed by specialists, tested electronically, and evaluated for resale into the used serviceable material market, where they provide a dramatically cheaper alternative to new parts for operating carriers. After the high-value components are stripped, after the hydraulic systems, the engines, the avionics are all gone. What remains is the airframe itself, and even this, the bare skeleton of a machine that crossed the Atlantic thousands of times, carries extraordinary value. The A320's airframe is composed of 72% aluminum and aluminum-lithium alloys, along with 9% steel and 6% titanium. And here's what makes this extraordinary. Recycling aluminum uses only 5% of the energy required to produce it from raw bauxite and cuts CO2 emissions by 95%. The fuselage isn't scrap, it's a stockpile. Once the airframe is cleared of all systems and interiors, industrial cutting teams move in. The cut material is sorted rigorously by alloy series. Aerospace aluminum isn't a single material, it's a family of precisely formulated alloys. The 2000 series alloys used in aircraft skins have different compositions than the 7000 series alloys in structural members. Mixing them degrades the final recycled material. Sorted aluminum is fed into melting furnaces at approximately 750 degrees Celsius. Additives are introduced to adjust the melt chemistry. The molten alloy is cast into ingots, and those ingots enter the supply chains of automotive manufacturers, construction companies, and industrial equipment producers. In a June 2025 breakthrough, Constellium and Tarmac Aerosave announced they had successfully remelted aluminum from retired commercial aircraft into new material, meeting full aerospace manufacturing specifications, meaning aircraft aluminum can now fly again in new aircraft after recycling, a world first. Here's the connection most people never make. The aluminum and steel recovered from scrapped aircraft doesn't just become car parts or building panels. A significant portion flows into the manufacturing of industrial hydraulic systems, the heavy presses, excavator arms, injection molding machines, and manufacturing robots that power modern industry. The steel recovered from aircraft landing gear, already rated for aerospace-grade impact loads, is particularly valued as raw material for high-strength hydraulic cylinder manufacturing. An aircraft's hydraulic system doesn't retire when the aircraft does, it transfers. The numbers that define modern aircraft recycling are remarkable. Tarmac Aerosave, the Airbus-owned recycling subsidiary operating in France and Spain, documents a 92% recovery rate on retired commercial aircraft by total weight. More than 99% of engine parts are recovered and reused. In March 2024, ATR Aircraft reported that its partnership with Tarmac achieved an 85.5% material recovery rate on retired regional aircraft, a record for that category. According to a 2025 peer-reviewed study published in Materials Circular Economy, more than 13,000 aircraft are projected to retire across commercial, military, and private sectors over the next 2 decades. That represents up to 44% of the current global fleet entering the recycling stream. The aircraft recycling industry collected $2 billion in aircraft parts revenue annually from the approximately 400 to 450 commercial aircraft reaching end of life each year. Here's what most people never consider: the hydraulic press stamping out automotive body panels in a German factory. There's a measurable chance that the high-strength steel in their hydraulic cylinders or the aluminum in their frames was once part of a 737 that flew 80,000 hours over 25 years. The aluminum that once formed a fuselage cruising at 35,000 feet will be melted and cast into components for the next generation of aircraft. The hydraulic actuators that once extended flaps over the Pacific will be overhauled and continue operating in industrial applications for decades more. This is not the end of an aircraft story. It's the beginning of its second life. Thanks for watching.